we can start the afternoon session of your workshop. I'd like to welcome everybody once again. Thank you very much for joining us, for those that are here at Inatel and also those that are online from the multiple platforms that you are broadcasting. I would like to welcome Professor Mohamed-Slim Alouini, which you present. He's talking about towards connecting the remaining 3+ billion unconnected. This is a very important topic for the Brazilian reality. We know that you have a million of people that are living without any kind of coverage, and find a solution to connect those that are not living the digital era today is one of our goals here at the XG Mobile. So Professor Mohamed-Slim Alouini was born in Tunis, Tunisia. He earned his PhD from the California Institute of Technology, Caltech, in 1998, before serving as a faculty member at the University of Minnesota and later at Texas A&M University at Qatar. In 2009, he became a founding faculty member at King Abdullah University of Science and Technology, KAUST, where he is currently the Al-Kawazimi Distinguished Professor of Electrical and Computer Engineering, and the holder of the UNESCO Chair on Education to Connect the Unconnected. Dr. Alouini is a fellow of the IEEE and the Optica, and his research interests encompass a wide array of research topics in wireless and satellite communication. He is currently particularly focused on addressing the technical challenges associated with information communication technologies in underserved regions, and is committed to bring the digital divide by taking issues related to the uneven distribution access to and utilization of ICT in rural, low-income, disaster-prone, and hard-to-reach areas. Professor Lin, thank you very much once again for joining us. The floor is yours.
Thank you very much, Luciano, for the very nice introduction and for inviting me and giving me the opportunity to share with you some of our work in my research group in this area on Connect the Unconnected. I would have, of course, liked to be with you. I visited Brazil a couple of times in the past. It was great trips for me, but it's a little bit a long trip for me towards the end of the semester, and unfortunately this time I will do it online. Actually, I realized more and more how important is this topic for Brazil, because actually today I am in Riyadh in a conference called Connecting the World from the Sky, organized by CST. CST is the spectrum regulator in Saudi Arabia, like Inatel, my understanding, in Brazil. And actually the president or the director of Inatel was in this conference from Brazil, and he explained the challenges of Brazil in Connect the Unconnected. So he gave a very good presentation and explained all the different projects in Brazil, and also how difficult is the terrain and the jungle, the Amazon. And so I understand that how relevant is this topic to a country as big and as diverse as Brazil. So obviously we are all now living in a world where we are expecting 6G. Probably you hear sometime the news that 6G is coming very soon. It's like we are a few years from 6G. When you look at our typical IEEE conferences, of course, the main focus is on Olympic records, on how we can go to faster data rate, how we can lower the latency, how we can basically increase the density of connected IoT device in smart cities. That's, of course, pushing the envelope type of, let's say, expectation that every generation had to go through. But from my perspective, and a few of us in the community, including Luciano, because I'm familiar with his work, we want also to look at other important aspect, which is trying to connect more the unconnected. We still live in a world where we have about 1/3 of the world population that is unconnected or underconnected. We are talking about like 2.6, 2.7 billion people. There are a variety of reasons. Not all of them are due only to coverage, but coverage is one aspect. And most of the areas that are affected by this digital divide are the rural, hard-to-reach, type of areas that are not basically getting good internet connectivity. And with that, clearly, there is a desire to make sure that in contrast to previous generation of wireless communication network, which were essentially driven by profit and financial perspective, we would like 6G to be at least in part driven by the SDGs, and that happened in a way because those of you who are familiar with the kind of the way standards are built and ITU operates, ITU already issued in late 2023 the so-called IMT 2030 document, and within that document clearly there is a new user scenario called ubiquitous connectivity. You can call it global connectivity, which is part of the expected performance or expected KPI from 6G, which means that we would like to be more digitally inclusive and make sure we connect more of the unconnected. And actually, in a way, we can make also our network more resilient. Why I would like to mention that? Because when we work on connecting the unconnected, connecting rural areas, hard to reach area, you are solving, in a way, many other problems. For instance, many areas that are extremely well connected can lose connectivity overnight because of a natural disaster like a flood, volcano eruptions, earthquake, etc. And basically, we have to deal with hundreds, if not thousands, of people unconnected overnight. And you need to bring connectivity, typically from the sky, as we'll see, from the space or the sky, to basically bring connectivity for the first respondents and the victims to make sure that they remain connected and get the right help at the critical time. Exploration is also an important aspect of connectivity because when you send people in the middle of nowhere, let's say for adventure or for scientific exploration in the Amazon, let's say, or in the Antarctica, obviously they if they want to video stream data in real time, that's connect and unconnect type of problem. Military mission tends to operate often in unconnected environment. IoT everywhere. This is an important concept that I would like to advocate for. When we say connect the unconnected, we are not talking only about connecting unconnected people, but we are talking about connecting unconnected zones or regions. Why? Because like we can talk about smart cities, we want to talk about smart rural areas, smart mountains, smart seas. We want to put IoT device everywhere, and we can use that for exploration, for environment monitoring, for extraction of natural resource. So basically, IoT should not be restricted to urban, highly dense environment for smart building and smart cities. It can be generalized to everywhere, and you need global connectivity to allow this to happen. Also, you may deal with the connect and connect type of problem in an urban environment when you have unpredictable traffic, when you have basically a surge of capacity for a final of a football match or an Olympic game over a period of time, where basically your network is designed for median type of traffic, and then suddenly you have the surge of capacity. So these people will be not able to connect if there is no extra capacity. So you need to bring this extra offloading capacity. Typically, again, this can be done by the sky. So that's also another application of the type of techniques we are advocating for. And finally, transportation systems can benefit quite a bit, or emerging transportation system. When we talk, for instance, about eVTOLs, about flying taxis, flying cars, these, of course, are not part of our today reality, but clearly it's expected that in a few years, maybe decade, our ecosystem, especially in the highly dense urban environment and mega cities, flying taxi would be part of the norm to kind of avoid congestions. And you need to connect this flying taxi at few hundred meters, and connecting them from the sky, from a satellite, or as we talk about, like a high to platform station, is probably the way to go. And finally, maritime environment is an ideal environment also, where we can talk about connected and connected, because 70% of the earth is covered by water, and obviously you need to cover all these maritime routes to bring connectivity to islands, as well all these boats and ships that are going through the seas. So that's just to kind of emphasize that when we talk about connected and connected, we are not talking about rural areas and about basic developing countries. We are talking about a multitude of other important applications that are beneficial to many sectors in pretty much every single country in the world. Now, from a technical point of view, what is one of the main issues we have to solve? I like to summarize it in these two keywords: backhaul challenge. So what is a backhaul challenge in my mind. It's summarized by this view graphs, where we see here the quality of experience. You can measure in bit rate and delay, whatever kind of quality of experience measure you would like to take, as function of the cost per user, focusing on remote low population density areas. So obviously, if you go with optical fiber cables, this is the right solution for urban, highly dense environment, because then you can basically get return on investment in this high dense urban environment. But I hope you all agree with me that it doesn't make much business sense to dig and basically lay hundreds, if not thousands, of kilometers of optical fiber cable to reach these remote, sparsely populated, um, often low income, rural, hard to reach areas. It just does make business sense. There is no return on investment, and mobile network operators are not going to do that, and will not base deploy equipment, and you end up with some coverage gaps. Now, satellites, of course, it's a classical way to connect over broad coverage areas. It's very successful for the TV broadcasting, one-way TV broadcasting. When it's go to two-way communication, like the Starlink, of course, it's being promising solution, but still quite expensive. I mean, this is not the solution that you can deploy in all of these low-income areas that need this kind of solution. But that's a good progress. So, but our ultimate objective is to kind of migrate towards this upper left corner. We can call this upper left corner the global connectivity holy grail. Basically, providing good enough high-speed broadband, let's call it, connectivity at a low cost, even for sparsely hard-to-reach density population areas. So this is kind of our ultimate objective. In order to achieve, let's say, this visionary statement made by Tesla 100 years ago. If you read carefully the statement made by Tesla, you will see that he was already pretty much thinking in a 5G or in a beyond 5G or 6G terms in 1919. So how can we do that? So one way to do that, and I think a very simple approach. This is not our invention. It has been kind of pursued by many research groups, I think, including probably Luciano group in Brazil and few other in Sweden, is to recycle the TV infrastructure. So TV towers are strategically located worldwide in on the top of hills and mountains, have good coverage using low power of the spectrum. So what about if we attach base station to these TV towers and capitalize on the low spectrum? We can create these macro cells, and indeed, it's a very good idea. Again, this has been kind of proposed in many papers. In one recent paper, we tried to combine this with massive MIMO and apply that to a particular province in Ethiopia, which suffers from deep digital divide. 5% only of people are connected. In this map, we see this province. In blue, high density population. In green, medium density population. In yellow, very low density populations. They have only 2 3G base stations in red. With that, they are covering, as I told you, only 5% connectivity in this region. So we said, what about if we capitalize on the 3 TV towers that happen to be in these 3 black spots here and attach to the massive MIMO type of technology? With that, right away, you can go from 5 to roughly 15%. Actually, if you migrate a little bit or move a little bit these TV towers towards a location where there is a higher density population, then you can go all the way 20%. So that's, in a way, a simple solution to kind of bring connectivity from very low to something a little bit better, but still insufficient and not enough to kind of really mitigate the digital divide. So bottom line, the main concept we are trying to argue for here, and I think if there's something I would like to take out of this talk, is probably this slide. What I'm trying to argue for is that we live in a world where we have different density populations in different parts of the world. We can live in some dense urban environment, like we may end up being in a very low density population maritime environment. And for every single environment, there is probably the right base station at the right altitude. That's really the main message we'd like to convey. Actually, we tried to kind of advocate for that in a paper published last year, published in T-Wireless. And what we proposed is to basically look at a particular deployment using stochastic geometry framework, assuming that we have users that follow an exponentially decreasing density of population, which is common and well-known kind of model that is used in population density type of studies. And then we said, how can we optimally connect these users, assuming that we have, let's say, 25 drones that in terms of density. So we can use either these 25 drones in a uniform fashion. Basically, we ignore that the user have a decreasing exponential density, or we can be smarter and assume that actually we should also deploy the drone according to the density of the user on the ground. But not only that, we'll make not only the density of drone decrease, but also we'll make the drone altitude increase as density decreases. Okay, so we try to do at all of these options. So this was modeled mathematically. You can look at, sorry, the equation have been removed here, but that's fine. So that was like an equation showing the density of users decreasing exponentially and density of drones also decreasing exponentially. But bottom line, the results are summarized in this graph. So what this graph or figure is showing the coverage probability as function of distance of a user from the center of the, let's say, of a city. So if you use uniform deployment of drone, which is obviously not the thing to do because you're ignoring that the user density is decreasing, you get the lowest coverage probability. If you use an exponentially decreasing density of drones, but at a single altitude, let's say 50 meter, 100 meter, 150 meter, you get better coverage, but still not as good as if you use a 3-tier type of deployment, which means you start with a low altitude, higher altitude, eventually go at the highest possible altitude to meet the fact that you are having a lower and lower density of user on the ground. So this is an illustration, or in a way a proof of our intuition that actually you need different altitude of base station to cover different density population on the ground. This leads us to the fact that you cannot keep relying on towers. Of course, you can use a lamppost or basically a tower in urban environment. You can go maybe to kind of a big mast, but at some point you cannot keep building hundreds of meters of towers. You need to start providing connectivity from the sky by attaching base station to flying platforms. So one of the solutions is to use tether balloon or tether airship. That's technology that is available. It's used lighter than air type of helium to make this platform float and stay aloft, basically. And then you can attach to the payload the base station, and with that you can cover large macro cell type of or provide large macro cell type of service. So as an example here, we looked at the disaster type of scenarios where you have user on the ground that lost connectivity. You send some drones to act as a flying base station. These drones need backhauling because at the end of the day, they need to be connected to the network. This backhaul is done through these tether balloons. And the problem that we looked at is how can we maximize the sum rate of this network. It's a 2-hop network, like user to drone, drone to balloon. The balloon is assumed to be connected to the internet. How do you maximize basically a sum rate of this network? By basically optimizing the association of the user to the drone, the association of the drone to the balloon, allocating the right power in the drones to the users, and also optimizing the location of the drone. So it's a basically multi-parameter optimization problem that one of my former students, Ahmed Shara, solved. And mathematically speaking, you are maximizing this sum of overall drones, and you have 2 hops, so you minimize over 2 hops, and you have all the kind of typical constraint you see in a network. And then basically, to make a long story short, we kind of solved the problem iteratively. First of all, we looked at the UAV placement type of optimization using shrink and realign algorithm. And then once the UAV position has been basically optimized, we associate to the right drone, we associate user to drones, and we allocate the right powers. With that, you can compare the performance of different type of allocations. If you do uniform allocation, you get basically this bad performance. If you do an optimization of the drone without power allocation, you get the red curve. And the ultimate solution, if you do optimal allocation of drone location, optimal power allocation, optimal association of user to drone and drone to balloon, you get the best possible sum rate you can get out of this network. So these are the kind of problem one can solve as soon as you start having base station with flexible location, with flexible power allocation, in contrast to a static base station on the ground where you can allocate power optimally, but you cannot change location in a dynamic fashion. So now, of course, you can try to gain in coverage, and to gain in coverage, you have to gain in altitude. And to gain in altitude, you need to go beyond few hundred meters to a couple of kilometers. That's what the tether balloon or tether airship gives you. You go to the so-called high altitude platform station, known also as high altitude pseudosatellites, in short, HAPS. These are flying platform operating in the stratosphere, somewhere around 20 kilometer altitude above the troposphere, above the weather. It's a nice sweet spot in terms of minimal wind over there. And then these kind of HAPs basically appear in different form and shapes. They can appear in the form of balloons, in the form of airships, in the form of fixed wings aircraft or gliders. It's a kind of an emerging field from an aeronautic perspective, and there are different companies trying to design and be successful at building these different HAPS type of solutions. And HAPS is not a telecom project. It's more an infrastructure project. It's a stratospheric infrastructure that can be used for multiple missions. We are not talking only about connectivity. Connectivity can be an important applications. For instance, here, assume you have a disaster, a flood in this particular region. The green kind of here beams are helping people that have been moved to refugee camp to connect them overnight because they have lost connectivity. For this other HAPS here, we are trying to connect IoT devices that are scattered in this remote region and for smart agriculture application. But HAPS is not only for the green telecom application. We can use them by attaching a camera to the payload and use them for border control. We can use them for environment monitoring using a LiDAR attached to the payload. We can also attach radar also for basically measuring height of water in the case of flood or something like that. So basically, it's a tower in the sky at 20 kilometers with a specific payload, and you can design your payload as you like, depending on the mission and application you are pursuing. So now, if you want, of course, to gain even higher coverage, you need to go even to higher altitude, and then we move from air to space. What do I mean by that? You kind of cross a so-called imaginary Karaman line. This Karaman line, roughly 100 plus kilometer, where basically gravity becomes negligible and the objects are not anymore quasi-stationary. They will have to be on orbit. And that we start talking about satellites, of course. And then you have a different family of satellites. You have the LEO satellites that are basically kind of go at a very fast speed if they are at low altitude. And the higher you go, ultimately you go to geosatellite, which if you are at 36,000 kilometers, you can be completely geosynchronous, geostationary, and you can look as if you are basically fixed with respect to the ground. So all of these solutions are being pursued. Of course, you are all aware of Starlink, OneWeb. The Chinese actually are very active with their G60 constellation, but also geosatellites. They have now new generation of very high throughput satellite like Jupiter from EchoStar or Viasat 1, 2, and 3. These are also all very important technologies that are there to help with global connectivity. Now, having said that, my argument, again, going back to the message I was trying to re-emphasize, is that we need all of these solutions. We need we need towers, we need basically hubs, we need satellites. Okay, so there is no one solution fits all. The density population will require different type of solutions and different kind of altitude. But I would like to emphasize the importance of, let's say, HAPS, at least for certain perspective. The perspective I would like to emphasize that of course, one of the important paradigm that we are trying to solve with the connectivity from space and sky is so-called direct to phone connectivity. How can we connect directly to our phones and not special phones, a satellite phone? We want to use our standard 5G, 6G phones to connect to satellite. This is not an easy problem, although, of course, Starlink, Apple are all trying these kind of different solutions. But we are not talking only here about texting. We are talking about full broadband connectivity. It is possible maybe with huge antennas, with maybe limited number of users. With HAPS, this can, when you talk about satellites, it's very complicated. When you talk about HAPS, it's much easier because HAPS is just at 20-kilometer altitude. It's not at 500 or 600-kilometer altitude like any LEO satellite constellation. So that's one aspect. Another important aspect is about like the let's say the management of the network. At the end of the day, a HAPS is an aircraft or an airship, which means it goes for a mission. It stays there for maybe a few weeks, maybe few months, depending on the endurance and autonomy it has, and then it comes back. When it comes back, it can be maintained, it can be upgraded, it can be eventually retired. In contrast to a satellite, when it's sent, is over, it's gone. Maybe you can upgrade the software, but then at some point it has to be retired in the space and becomes space debris, and you have to find a solution to the space debris. So it's in a way a more complicated problem from a long-term sustainability and management. So these are 2 points that I would like sometime to emphasize about the advantage of HAPS, and that's why we have to pay attention to this emerging technology and don't think that a satellite and Starlink is going to solve all the rural connectivity type of problems. So as a way to kind of demonstrate that this is not science fiction in a way, as you may know, there has been 2 interesting projects that started about 10 years ago by Facebook and Google, the Loon project and the Aquila project. I mean, we can talk maybe during the Q&A part why they didn't succeed that much, but at the end of the day, they were able to demonstrate the capability of talking to a HAPS from the ground, and Loon was able to run a 4G network from the stratosphere in Kenya and in Peru. So this is a possible thing to do. Is not science fiction. You can run a cellular network from the stratosphere. Actually, relatively recently, CST here in Saudi Arabia, in collaboration with Deutsche Telekom and SPL. SPL is a stratospheric platform startup based in Cambridge, UK. Did a demo. We contributed to this experiment, and this experiment was documented in this IEEE Open Journal Communication Society paper, where basically 5G type of trial was done from a HAPS. And basically, just as a very simple example here, we are showing kind of a car moving away from a base station on the ground with the blue link illustrating here the connection between the kind of terrestrial base station and the car, and the HAPS connecting to the base station via another kind of purple link. What you notice is as the car moves away, of course, the quality of the service, like the throughput and spectral efficiency of the blue link, the terrestrial link, goes down because at some point you don't have a good coverage anymore from the ground, whereas the coverage from the sky maintains a very good coverage over long distances, including actually some colleagues did calls from maritime and helicopter, and that's clear line of sight type of situation, and clearly HAPS has clear advantage over large coverage areas. Using again standard phones, so just to change your SIM card and with the SIM card on the HAPS, and that's pretty much it, Now, what kind of problem you can solve when you start looking at HAPS type of problems? One typical problem is basically how to allocate resource optimally in integrated space, satellites, air HABs, and ground networks. So here an example of a paper with my PhD students, Shasha Liu, in collaboration with my colleague, Professor Haytham Dahrouj. And the idea, we have ground users. These ground users are in different environment, and they can choose to connect either to a terrestrial base station or to a HABs. And the question is how to do that, and how to do that in an optimal way to maximize, let's say, the sum rate of this network. So that's kind of the mathematical equation, trying to maximize, again, the sum rate and allocate the user to the right type of base station, using, as usual, the standard constraint on power, payload, and association. So just to make a long story short, what we show here is an area including an urban environment, here in the lower left corner, a suburban area, lower density population, upper right corner, and the rural area in between. It's a downlink situation. We have terrestrial base stations scattered with higher density, of course, in urban environment, less in suburban, and very few in rural. And we have a HABs in the middle here. We start with the HABs with very low power, minus 4 dB watt, downlink. And with that, the urban users are connected exclusively to the urban base station, the suburban user to the suburban base station. We are able to connect only one rural user because of the poor budget link with a very limited power coming from the HABs. You increase the HABs power from minus 40 dB watt to 10 dB watt, you start connecting more of these rural users in red. You further increase the power available in the HABs to 30 dB watt. The good news, not only do you connect all the rural users that are scattered in this large rural region, but also you are able to offer better link to some of the urban and suburban users, which means a solution coming from the sky can help you not only connect the unconnected, which is maybe its primary mission, but also super connect the connected, which means you may end up having users in urban environment in a not a very good spot with obstruction behind a building or something like that, that will benefit from a beam coming from the sky, because that beam will leave a better line of sight type of condition compared to any other kind of terrestrial base station in that neighborhood. So that's the beauty of a HABs. It's a stratospheric infrastructure that can help over a large area, it can be few tens of kilometers of coverage, that can help the most intended use, which are the ground rural user, but also some of the suburban, some of the urban users. This work has been generalized to multiple HABs deployment over larger area. And then what we showed in this follow-up paper, that basically, of course, the more HABs you add, the more fair is the network. Basically, what we are showing here, from 0 HABs, you have a large number of users below a certain minimum SANR. And basically, as you increase the number of HABs to 3 HABs, the minimum SANR tends to increase, which means you give better and better coverage throughout the region of coverage. So that's the ultimate objective. The ultimate objective is not to have a single HABs, but over large area, like we talk about a satellite mega constellation, we can talk about HABs constellations to cover large areas and basically create networks that are reliable and basically regardless of the nature of the ground environment, urban, suburban, or rural. So that's an illustration of how the connectivity improves. 0 HABs, you have only users connect to the ground networks in magenta, and then a single HABs shows up. Then you have the green user being connected now to the first HABs. Then basically you have a second HABs in blue, so you have some user connect to the first HABs, some user connect to second HABs, and some urban and suburban environment benefiting from that. With the 3 HABs, you have basically some user connect to the third HABs in red, green, users, blue users, and even suburban users can benefit from that. And some also urban users benefit from the third hubs. Again, that's generalization of what we did with the single hubs to multiple hubs, trying to illustrate this concept we call connected and connected and super connecting the connected. Now, of course, machine learning is a very popular topic these days. All what I showed earlier was relying on standard optimization iterative algorithms. So like any student, Shasha was very interested like trying to develop machine learning based approach. And so basically she trained kind of a deep neural network using a kind of the so-called assembling approach, where basically she kind of run this optimization over multiple parallel small DNN to avoid this kind of overfitting problems and take every time the best potential solution. And with that, she showed that with this approach, with eDNN, ensemble DNN, you can indeed outperform classical approach, at least from a power allocation perspective. We need to look at like the weights of the beamforming type of optimization. But for optimal power allocation, the machine learning based approach outperform classical approach, and actually can do it in a relatively fast amount of time, as shown here. The eDNN can do it in basically 26 milliseconds on the computer used by Shasha, our students, whereas a classical basically optimization approach will take much longer time. So now I would like to go to the second part of my talk, to kind of talk about another interesting, at least from my perspective, technology that can contribute to this aerial and space network paradigm. This technology, many of you probably know it. It has been there for many years already, or many decades, I would even say. It's free space optics. This is a technology that is quite mature. There are many companies that sell FSO product for terrestrial applications, but it struggled, let's be honest, to make it to the big market or massive market deployment for ground application, for a very simple reason that it's quite sensitive to fog, to weather conditions, to alignment type of issues. Now, although there is a little bit of progress on FSO for terrestrial application, I believe that one of the things that will make FSO maybe more successful is to combine FSO with this aerial and space links. Why? Because as soon as you start talking about aerial and space links, you start looking at a very important constraint that everyone who know avionics and aerospace can relate to, is known as a swap constraint. So what is a swap constraint? Swap constraints stand for size, weight, and power. So every time you try to lift something, so you have a payload in a satellite, in an aircraft, in a HAPS, you ask yourself, how big is this thing, dimension-wise? How heavy is it? And how much power does it need to operate properly? Swap. So FSO in this context is great. It beats RF without any question. It's much more compact. You're operating at a high frequency, small wavelength, so every single photonic device can be smaller than RF devices. It's more energy efficient, and it can give tremendous data rates in comparison to RF type of solutions for the same size. So bottom line, the ultimate kind of vision that we have is that FSO can be used not only for inter-satellite links, which is already happening with, for example, Starlink, but actually as a feeder link between the ground and space. So the paradigm we have in mind is that you have this aerial base station attached to a satellite, to a HAPS, to a certain extent to a TV tower, for that matter. And then basically we have this kind of base station that use RF technology with massive MIMO to create these beams. These beams are reconfigurable, readjusted. You can send them to wherever traffic is needed, okay? But then all these beam traffic can be hands of them. Each one can carry 10 gigabit. So together you can create, when you multiplex all these beam, basically a feeder link of few terabit per second. That's what is now carried by the Ka band in current very high throughput satellite. Ka band is a band that is under heavy kind of demand by different competitors, like IMT wants that band. Actually, Ka band is also under demand by the satellite themselves to use it for to use it for the user link that are currently using KU band, which is kind of running out of spectrum. So basically, the idea is to use free space optics as a feeder link between this airborne, basically base station and the ground. So it's basically a ground to air or ground to space type of links using free space laser links. By the way, this is not science fiction. It has been kind of demonstrated already by DLR in Germany, but NICT in Japan, MIT Lincoln Lab in the US. So it is there, but it needs to be, of course, industrialized and eventually commercialized so that we see a massive deployment of this technology in the near future. Now, one of the issue, to address, as I mentioned earlier, like for the ground, for the air and space, is how to deal or how FSO has to deal with atmospheric turbulence. So atmospheric turbulence is these kind of air bubbles that creates a kind of different layer in the atmosphere that make the kind of light beam, let's say, kind of basically diverge. And at the end of the day, the end result is that at the receiver end, the beam basically opens up or kind of lose focus, and also we start seeing the so-called beam wandering effect. So we this is kind of from an SNR perspective, you end up having basically scintillation or fading. One way to mitigate that is to use adaptive optics. Is a technique that has been used in the context of basically telescopy, have been kind of borrowed in the context of telecommunication to correct the phase of the kind of degraded channel that went through a turbulent environment using this array of deformable mirrors. This is kind of a photo taken from the lab of one of my colleagues. You see the clean beam over an atmospheric turbulent environment, you get this distorted beam. After adaptive optic post compensations, you can clean or correct the beam to a certain extent. If you have some basically constraint on the receiver end from, let's say, swap, size, weight, and power, so you can put the compensation up front. You do AO pre-compensations, assuming that you know ahead of time roughly how the turbulence looks like. So you pre-distort the beam in a way that when it goes to turbulence, you end up with a nearly pure beam. So adaptive optics is not the only way, but one promising way to mitigate the effect of turbulence. What we did in one recent paper, or relatively recent paper published last year, we kind of analyzed the performance of FSO, ground to air, air to ground, also air to air for HAPS type of links under realistic atmospheric turbulence and pointing error, because you have to also make sure that you take into account that not everything is perfectly pointed. And just to make a long story short, we were able to come up with a kind of a nice analytical framework to evaluate the performance of these links. And some of the key results that we were able to obtain are summarized in this figure, where we show the performance of the uplink in blue. We see here, for instance, like with adaptive optics, you have much better performance with basically adaptive optics for all the case, uplink, downlink, and horizontal link. So uplink is, of course, ground to HAPS, downlink HAPS to ground, and then horizontal is HAPS to HAPS. So one thing we notice here, the uplink tends to be worse than the downlink, which can be explained by the fact that atmospheric turbulence tends to be stronger from an intensity perspective in the lower part of the atmosphere. So basically, when you transmit an uplink right away, you get hit by very strong turbulences, and at the end of the day, this cumulatively can affect the overall performance of the link. Downlink, you start seeing the effect of turbulence only towards the end of your propagation path. Now, the good news is when you are above the troposphere, basically the stratosphere, where HAPS sit at 20 kilometers or so, there is no turbulence anymore. The only problem you have to solve is a pointing problem, because you are way above the atmosphere and turbulence, and that's make it very interesting to adopt free space optic for anything above 20 kilometers. And that explains why Starlink, and this is already done, is using FSO for their inter-satellite links, but this can be used also for all kind of inter-HAPS communications. Now, how can you also mitigate the effect of turbulence? You can also use MIMO technology by using multiple lasers and multiple detectors. So, as a follow-up paper with my former students Emre Ziddini and my collaborator Professor Yaltin Ata, we're able to show how multiple input, multiple output system, meaning by that, let's say a 2x2 type of transmitter and receiver operating in the type of ground to air type of environment from atmospheric turbulence and pointing error can benefit from MIMO by kind of getting quite a bit of gain in terms of outs probability. And of course, the higher the elevation, the more is the effect of turbulence. And we have to be also realistic. In this other paper with my former postdoc, we try also to look at the effect of correlation because MIMO is great. The potential of MIMO is great, like it is the case in RF. But it's great if you assume that the link are completely independent. Reality of things is you may end up having some correlation between the different links, so you cannot have full diversity. So in this paper, what Richa was able to achieve, she kind of analyzed the performance of the MIMO system under a certain level of correlation, and she indeed showed that you have a slight degradation. So from an ideal kind of black type of curves, you go to slightly higher out probability in red, assuming a certain level of correlation. So bottom line, I would like to conclude now and give some time for questions. This is the vision, or at least one vision we have for future aerial network or integrated ground air space network that can help connect the unconnected. We are talking about a constellation of hubs that can be used to cover wide areas. These hubs can be interconnected with FSO links. They can be connected to the ground via ground feeder links or to the space via FSO feeder link connected to satellites. Satellite being also still part of the equation. We cannot solve all the problem only with satellite or with hubs, but we'll have some hubs deployment, some satellite deployment working in collaboration to cover different density population areas. And again, I would like to re-emphasize, beyond the fact that hubs are not going to be used only for connectivity, as I mentioned earlier, that's a multi-mission type of infrastructure. But if you focus on the connectivity, we are not only focusing on connecting the unconnected people, we are also focusing on connecting the unconnected area in general, because we believe that many of these unconnected area can benefit from all kinds of sensing capabilities for a variety of exploration, disaster prediction, and so on and so forth. With that, I would like to conclude my talk by kind of emphasizing that air and space network is growing topic at a rapid pace for land, sea, and end user terminal deployed not only in rural and developing countries, but also for emergency post-disaster scenarios, for aeronautical maritime type of vehicles, and for urban offloading broadband communication scenarios. I believe also that FSO, which struggled quite a bit to make it to the, let's say, mass market for terrestrial application, has an opportunity to grow and capitalize on this emerging air and space network paradigm. And with that, for those of us doing research in these two topics, there's plenty of interesting research problems in the ground air-space network paradigm, near space hubs paradigm as also an interesting new niche, as well as FSO for these type of networks. With that, I would like to thank you, and I invite you to maybe follow some of our papers and research activities in our research group webpage. My students also try to create video articles summarizing their article in YouTube videos. And we have, as Luciano mentioned, established a couple of years ago a UNESCO share focusing on connect the unconnected, not only from a research perspective, but also from education. We run many times ICTP type of with ICTP, some workshops, and Luciano was one of our guest speakers there, to basically try to promote technologies and education in the context of connecting the unconnected. With all that, I would like to thank you all and leave you with this inspiring visionary statement made by Tesla 100 years ago. Thank you again for the invitation and for your attention, and I'll be happy to take some questions.
Thank you very much, Professor Slim. Thank you for the inspiring presentation. Very nice topics. We do have some time for questions, which can be sent by us online for those that are not here, and also be asked here by the public here in the auditorium. So if you have some questions, please raise your hand. There is one from the audience online. So there is a question from João Gabriel. Professor, as far as you have seen, who's offering more connection, government or private organization? Also, do you know what's most used application by the users?
I'm not sure if I understand the question. Like, who's supporting more, private or government?
Yes, exactly.
For
Who
like
is
rural.
providing? Yeah, who is providing the connectivity for remote areas more intensely? Government or private companies? And
For
what
rural
are the user
connectivity.
cases?
For rural connectivity, you mean?
Yes, yes, for remote areas. Yes.
This is a very good question. This is a very good question. I think it's, to my best knowledge, the best example I have seen are when there is partnership between government and private. I'll give you an example. Let's take India as, to me, one kind of quite successful example. So in India, what they are doing, at least my understanding of it, the government is committed to connect by fiber optic what I don't know the exact terminology in Indian language, but in their kind of framework, let's call them big villages. So that, let's say they have different categories: cities, big villages, and below that small villages and rural areas. What the government commit to, they will connect big villages with fiber optic. Now, around big villages, there are many other small villages. They give opportunity to private companies to basically get some kind of deals with a maybe kind of reduced license fee, kind of operator slash private companies partnership to get access to the fiber optic and do a backhaul, let's say 10 kilometer, 15 kilometers from this grand big village to smaller rural communities where they deploy Wi-Fi and license bands type of deployment. And the companies make money, these small companies, using local entrepreneurs, like maybe someone there who is kind of having a small store in this community, who will run the small wireless mesh, Wi-Fi mesh, and people can connect to that. So it's kind of a partnership. In South Africa, by the way, they have not exactly the same, but similar model where basically the network operator are in charge of basically reaching the main areas. But then when you go to township or like kind of, let's say in Brazil, maybe it's called favelas, that part of area will be done in a wireless Wi-Fi mesh type of deployment. And license band, low cost. So basically everyone, because sometimes the problem is not really coverage. Maybe the coverage is there, but maybe too expensive for people. So you want to come up with a very low cost solution, use a license band like Wi-Fi, for example, mesh over maybe a few hundreds meters to cover a particular low income neighborhood. So in my opinion, the best way is to basically rely on partnership between government and rural areas, government and private entities. Because, and I'll conclude, the government has an objective to bring connectivity to as many people as possible, right? Because that's kind of the government job. And the private want to make money, so they need to have special treatment, special advantage from the government to be able to achieve that and be able to give connectivity at an affordable cost while making some money.
Okay, thank you. Another question is regarding the standardization. This morning, we heard from Professor Ari from University of Oulu that the manufacturers and also operators are pushing 6G to be a kind of 5G in terms of physical layers, but operating in a slightly higher frequency, around 50 gigahertz. Do you think that this approach will make 6G a success? Is that flexible enough to cover all the user case that you are seeing today?
I'm not sure. Are you sure that this is what he said? I mean, like, I mean, to be honest, maybe depends on the context. Let's be, because sometimes it depends on what we are talking about. But to be honest, I'm not maybe I cannot argue. I cannot say that I'm following every single development 5G and 6G. But one thing I think there is a consensus about. I'm not talking about research here. I mean, research. There is quite a bit of interesting work on millimeter wave, on terahertz. No question about that. But in terms of deployment, when you talk to mobile network operator, I think most of them will tell you millimeter wave didn't pick up. So I really don't see them doing the same mistake in 6G and investing in even higher frequencies. Honestly, I mean, again, maybe for 7G, 8G, at some point we need to use, or maybe very specific locations, stadiums, super high density coverage when you need like a very high speed hotspots. But my feeling is, in the contrast, there is a big emphasis on mid band, on basically the 6 gigahertz, 7 gigahertz, and also doing better job at the 3 and 4 gigahertz band, trying to do better and better job on the lower part of the spectrum. This is regardless of rural, not rural. This is just to kind of expand and bring more capacity even to urban environment while being economically viable. That's, I think, the feedback I'm getting from the MNOs. Again, research, there is still, of course, a lot of interesting research in millimeter wave communication, terahertz, and so on. But that's my feel. And then, Luciano, you are of course very well aware of this, and you are one of the leaders on kind of pushing this. I think for rural connectivity, we need lower and lower part of the spectrum. I mean, like we want to go to TV white space and want to make it part of IMT because we want to kind of make it even somehow enlarged or lightly licensed so that we have this nice front beach type of spectrum for long coverage over long distance. So that's what we need in rural connectivity. That's really what help to connect larger regions.
Okay. Any other question from the public? We do have time for more than one question. So I do have one, Professor Slim, so you can close it. You have been talking about connectivity in remote areas in workshop organized by Professor Mitchell from Wits University in South Africa last year. And then you had the opportunity to talk it again with within the conference that you organized in Morocco. And now we are here in Brazil talking about, once again, how we can connect people around the world. How do you feel that those efforts are being successful? Are we being heard around the world or not? In other
Very
question,
good.
will 6G cover everybody or not?
I think definitely. What I can tell you, I see difference. I start on this topic, I would say, not by accident, but not really by. I mean, yes, it was by accident. In a way, I was involved in the African Academy of Science, and I was giving a talk on this. And I started about 10 years ago focusing on that. At that time, honestly, it was below radar screen. No one even talked about that. You go to ICC, Globcom, any one of these conferences, it kind of unheard topic. Of course, ITU, by that time, they still talk about connect the unconnected, digital divide. But when you go to technical IEEE conference, it was not there as a topic. In between, a lot of things have happened, including COVID, that showed how important is connectivity. So, I mean, as an illustration of that, as I mentioned in my talk, when you look at IMT 2030, which is the official ITU document, there is ubiquitous connectivity as a requirement. So there is a clear mandate for next generation of wireless communication system to do a better effort on connecting more of the unconnected. And that's why there is now within 3GPP NTN. I mean, before 5G, there was no NTN at all. I mean, like these were different silos. Satellite communication were working on their own world, cellular working on their own world, and they don't even talk to each other. Now they have to work to each other because actually they have to unite forces and integrate their network to reap the benefit of the scale of both systems, to allow our phone to connect to a terrestrial base station, to a HAPS, or to a satellite in a seamless fashion. So definitely I see progress. I see that we are going the right direction. Are we going to solve all the problems by 2030? Probably not, but definitely we are going in the right direction. And what I would like to maybe conclude with, Luciano, is not only a technical problem. I mean, let's assume you cover the whole globe. I mean, it can happen, right? But it has to be also affordable, because people have to be able to pay for the service, and also accessible. Like, how to explain. I mean, like, I think you probably understand that there are people who are not skilled at using phone, laptops. The content itself maybe is not relevant to them because they don't read English or Portuguese, or they don't find content that is relevant to their native language. So beyond the technical aspect and engineering and satellite and HAPS, affordability and accessibility from a content perspective and skill set to use as simple as a phone is also part of the issue that we are trying to solve here.
Okay, thank you very much, Professor Slim, for the time. Thank you very much for supporting our workshop. It was really, really enlightful to hear you today. Thank you very much.
Thank you, Luciano. Thank you for everyone for attending the talk. Thank you.
Okay, so this concludes your second keynote speaker from the day. We will have a break now, and we will be back at 3 p.m. with our, I'm sorry, looking to 3:30. Yes, exactly. With our second technical section. Thank you very much.